good to be here, talking to a Foresight group. It's, I guess, my first face-to-face talk to a group in 3 years, having spent a lot of time in COVID lockdown in England. I did use my status as a co-founder of the Foresight Institute to negotiate for a little bit more time, which I will use in part to give some context, some perspective on what drew me out of the AI area, which is where I've been in the last 7 years, asking where does AI go as it goes in the directions it seems to be going, broadly speaking. Often the Future of Humanity Institute at Oxford and in the orbit of DeepMind. So what dragged me back was realizing that after all of this time, people who are concerned about the long-term future have not taken account of what physics tells us about what can be built using atomically precise machinery that can, among other things, be used to build atomically precise machinery and a wide range of high-performance products. I see the effective altruism movement thinking about the future centuries, and assuming that we will still be making, for example, spacecraft out of sheet metal. Implicitly assuming that, not explicitly. So why has there been a failure to update on this possibility? My conclusion was that you can stand around talking about it and putting out texts on applied physics, all that you want, but without a clear and vivid picture of future prospects, they will not be understood. Without a community of people who are visibly working toward those purposes, they won't be understood. So accelerating progress toward advanced molecular machinery, building on the work being done by people in this room, making it clear what some of the paths forward are and where they lead, I think can make a tremendous difference to the human future, and I guess I could incidentally say should greatly increase funding for work in molecular machines. So, how to make these things visible and clear? Well, we need simulations, we need design environments, we need to be able to go beyond building, designing and building simple machines to building complex systems. So we need a new name. If anyone has a better name than MSEP for something that serves as a molecular systems engineering platform, that would be great. But a number of points here. I've already said something about concrete vision and goals and why those are important. I'd like to talk about design by refinement, top-down design as a way of thinking about complex systems and how to develop them. The different worlds of DNA, protein, and dense covalent structures as media for design. And then, since the topic is a specific plan, a specific approach, a specific project for building a design platform, talk about the virtues of open architecture and what I'm calling large surface area in making that work well. And finally, an invitation to contribute, where the main question will be, I barely touched this. Whoop. Okay, this is mysterious. There was a switch on the side of a computer at MIT which was attached to a wire that led nowhere, and it had a switch that in one position it said magic, and in the other position it said more magic. It wasn't connected to anything, but if you turned the switch, the computer failed. Okay, so yes, that's dangerous. I think we're okay. Uh-oh. Anyway, the invitation to contribute, what we're most interested in is what people need to do their work better, and what chunks of functionality should be built that we don't have, and what chunks of functionality should be brought into the same workspace so we can better design systems. Okay. No, that is not advancing. This is not in a presentation mode at the moment. There we go. Thank you. Yeah, so I wanted to incorporate by reference a whole lot of earlier talks which have touched on very crucial themes, and then a 3 p.m. cutoff because I actually had to finish the presentation, turned it in. So it's been known for a while that dense covalent machines, structures where you do not have conformational degrees of freedom, can be used to build machines that are like those that we see in the macroscopic world. In a car, you'll find a transmission that has a planetary gear and a universal joint and differential gears that enable the parts to move together and work as a system. Well, you can do systems with the kinematics and function and extraordinarily high frequencies like gigahertz range and extremely high power densities, many megawatts per cubic centimeter because of elementary scaling laws. You make planetary gears, universal joints, differential gears. But all of these were designed on workstations that by present standards have no computational capacity at all at Xerox PARC in 1992. So why have we not seen more of this kind of thing? Why did this basically stall at simple machines? And the answer is there are no good design tools. These things easy to design? Yes. They're fairly easy, even with point and click, atom by atom, copy, paste, maneuver, draw bonds. But it's fun. And simulations work very well because they're insensitive to small differences in energy. So they are very nice in terms of what the physics tells us about their performance and are going to be characteristic, I think there's every reason to believe, of important technologies at some point. But they're not understood, much less the systems that can be built with them. So a little closer to the present and implementability. This is a diagram of 3 configurations of a device that is the framework for a 3D printer, a positional chemistry system, an additive manufacturing system. And it has a number of virtues. It has surface area for a certain kind of motor device. It has interfaces and geometry that enables a rather stiff structure, low amplitude of thermal vibrations for given modulus of elasticity of the materials. But this one dates from 2015. Was presented somewhat before that at one DOE workshop and then in a follow-up workshop 2015 that was organized by Adam Marblestone at the University of Cambridge. That's what led to the funding that went to Andrew Turbefield and William Shih working on the 3D, the two-dimensional positioning mechanism using DNA origami and strand-based actuation. But do you want to use protein or DNA? What are the consequences of those? Stiffness, thermal fluctuations, components, kinematics, dynamics. It's not easy with available design tools. And I would like to have a little aside advertisement for protein. This is a deadly weapon. It's made of a biopolymer, keratin, it's protein. And you can tell something about its mechanical properties from its acoustic properties. And a key fact, if you're interested in machines that can position things precisely in the presence of thermal fluctuations, is that this has a modulus of elasticity something like 100 times that of DNA. That means the amplitude of thermal fluctuations, goes to the square root, is 10 times smaller for an equivalent shape with protein. That means that the area, circular error probable, the RMS footprint, is 100 times smaller, which makes a big difference. You can get another order of magnitude or more by going to strong covalent solids, but proteins get you a long way. So design by refinement. You need to have a concept and go somewhere with it. So here's a concept, 3D printer. You need X, Y, Z control and some kind of thing that the motion of which results in material somehow being deposited. There are a lot of ways of doing that. The configuration that I showed there is an example of a concept for a design. It's a mechanical concept. It's not analyzed numerically, but the geometry is the right kind of geometry to provide good performance. To take that further, one would want to have a coarse-grained elastic model of the structure to get more detailed specification of shapes and so on to meet the criteria for adequate stiffness. Need a motor. Well, 2D interface with a set of azobenzene molecules on it that are tuned to or can get energy from a light antenna from 3 different wavelengths is enough to make 3 independently controllable, reversible stepper motors, which can be reliable in the presence of photo bleaching and crosstalk. So it's a neat scheme, patentable, in fact patented, and if you want to look into that, it's a really cool way of making a reliable motor that's light actuated. And the trick there was that azobenzenes used to be activated in the violet to ultraviolet range and to switch back to relax thermally to their trans state in a time on the order of an hour. Advances in 2011, 2012 got the wavelength, the energy required down to the red or later infrared range, and the reverse switching time tunable down to nanoseconds, which is what makes these practical for a fast stepper motor. So general pattern, concept, thinking in terms of shape, moving beyond that to solid bodies, where at that point one can start doing physical modeling. Elastic body models, a good way to do that in the context of a uniform system of looking at, for modeling molecular systems is with an elastic network model, which is not quite as, doesn't have quite the fidelity of a finite element model. It doesn't capture the Poisson's ratio, but it can capture elastic modulus and the considerations that matter most for design, and in a way that's continuous with shapes that can be made to, well, the key point is that it fits with coarse-grained atomistic modeling. You can have one modeling universe that describes both large continua and actual atomistic detail. You can live in the same modeling world. So moving beyond simple structures, we start moving into the world of computer-aided design. Complex systems have a lot of parts. The parts work together. They have shapes, they have elastic properties, they have kinematics, they have forces, torques, and so on. The computer-aided design world has been working this problem for decades, and they have ways of systematically representing compositions of parts and keeping track of things like the computational models that tell us about the performance of those parts. And the thing on the left there is called a model tree. And it's important to be able to do that because if one has ambitious aspirations, eventually you're building things that are very complex. So comments on DNA, protein, and dense covalent structures. We have CAD Nano, which serves the DNA engineering community. I gather it's the most popular software at this point, though it's an area field in rapid flux. You'll note here that it was embedded as a Maya plugin. I have the old capitalization there. So that's just illustrates the fact that one can have a package that has a lot of complex domain-specific information, in this case about how to design DNA origami structures, and it can then be embedded in a range of different environments for visualization and manipulation. We'll be talking about a different environment for embedding this kind of functionality in a few moments. Another area is one thing that's very useful is, of course, coarse-grained model like OxDNA, making these design loops work well. Protein engineering, another area where there is a lively community. Rosetta has developed design software for doing work in this domain. I'm told that protein engineering software and DNA design software together don't really work together. One can make substantial progress by just having the shape of a protein molecule embedded in the DNA world so that you can make sure that the DNA fits geometrically the shape of the protein. Forget about actually modeling anything in terms of forces, but just the excluded volume. I think that's kind of shocking. Surely where we want to go is to combine our different biomolecular technologies to use, for example, the mechanical properties and chemical design flexibility of proteins, and the ability to make huge addressable structures with DNA origami. Those need to be brought together systematically and well. How else are we going to make really large aperiodic protein structures? Well, there are ways, but this may be a very attractive way. We need to bring these tools into the same environment, make the tools work together. Now, as a segue to where I'm going in a moment here, I would note that this picture is actually not a picture of something from the Rosetta design, but from Foldit, which comes out of the same group. And Foldit is a citizen science game. It has more than 700,000, I don't know how many players on any given day, but 700,000 registered users. So the citizen science community is very interested in playing with the molecular world. So this now moves to the next question. What about the world of things we can't make? Things that physics tells us we will want to make, things that we will be able to make along the path that we're following, but things that no one can make. No one is going to pay you to design things usually that can't be made, not in industry, only in the more theoretical activities in academia. So how does one make progress in exploring this world and getting a sense of where we're going, then perhaps working backward to bridge the gap between biomolecular machines, positional chemistry, working perhaps with dense, non-covalent, but but ionic solids or metal oxide solids that can be built in aqueous solutions and have a modulus that's much higher than protein, much finer grained. They're bridging technologies. So how could we get a clear picture, a lot of work done, whole lot of time going into designing and modeling systems like this? Think Minecraft. Millions and millions of users. They're given this world which doesn't look like any real world. It's a bunch of blocks with a very simple-minded kind of physics. They added something called redstone, which allows one to build machines, robots, working Rubik's cubes, all sorts of crazy stuff in Minecraft. Now, if Minecraft has millions and millions of users, and Foldit has 700,000 people who've at least downloaded it and registered it, I think we might be able to get a substantial user base playing around with what I will guarantee you are fun things to build, with blocks where you can point at them and say, look, I made this thing, and this is what how physics tells us it will work. See, the community curation has certified that the simulations are appropriately done. It's a proper member of the repository of designs. It's better than anything that was there before, or it's the first implementation of a certain kind of machine, and you talk about it on social media, and it goes up on the leaderboard, and you have more friends come in, and they play with it, and they say this is fun. And perhaps you build out not a Minecraft city, but a molecular systems engineering platform based, at least that would be under the hood. I'm sure the name that you'd see is different. It would be something on that platform that would be a view of intricate future technologies that would be clear and concrete and could have videos instead of being science fiction bullshit. I'm very tired of the science fiction bullshit. It pretty much ate everything for a decade or two. Okay, so that's the gamified end of the spectrum. So you have computational chemistry at one end and games at the other, and the computational chemistry underlies the games. Open architecture, large surface area. Want to build on free, permissively licensed open source software. The right thing to build on, I concluded, and I tried to talk myself out of this just for exercise and came back to the conclusion, which is you want to build on a game engine. And there is a rising star in the game engine world. It is the high-quality open source game engine called Godot. Godot as in waiting for Godot, meaning you'll wait forever for all the features to appear. It has a large enthusiastic user base. It has capabilities for rendering and manipulation and interaction and user interface building. And I did not touch the machine at all. I touched the cow horn, and it jostled the edge of the computer and my watch, and the watch is touching this wire here. This is more magic. Flick the switch and it will stop. Now, okay, so Godot. It's basically C++ plus plugins and IPC communication with other things. It has a scripting language. It has a native scripting language. What we're going to be doing is replacing that with Python. And that makes it easier to integrate beautiful graphics from PyMol, not just picking up PyMol, but because of issues with shaders and various things, but using PyMol as a major leg up in getting high quality, publication quality, highly informative graphics. So that combination gives one malleable user interfaces, visualization, interaction, et cetera, and Python scripting for everybody and for interfacing with lots of existing packages, like, for example, LAMPS. And LAMPS, in turn, the large-scale atomic molecular massively parallel simulator, supports favorites of the protein engineering community like AMBER and CHARM, OxDNA, though it's apparently a very slow implementation, but I am told that it will be easy to use the certified high-efficiency OxDNA and interface that instead of going through LAMPS on that. And handles rigid body mechanics and custom force fields, and all of these can be made to live in the same world with, take your pick of favorite quantum modeling package. Live in the same world through an abstraction used in the atomic simulation environment, which I eventually decided was too heavyweight in itself, but has this cool abstraction, which is you have a thing that you call a calculator. LAMPS in a particular mode would be a calculator, Quantum Espresso would be a calculator, OxDNA would be a calculator. And your authoritative source of information on the configuration of the world is on your side of the fence, and you tell these different calculators where the particles are that they're supposed to be thinking about. They think about it a while, they come back and tell you the forces on the particles. You put those together, add some other calculated forces that you made up, like something that simulates the force of a motor, that's not a real physical motor, but represents a boundary condition from a larger system. And you do a relaxation step or integrate the equations of motion forward a step. That gives you new positions. You send those out to the calculator again. Very flexible, very clean, very extensible. So picture here is core platform, graphics, manipulation, et cetera, et cetera, et cetera. And when I speak of surface area, I mean surface area for contributions, things that can be built in parallel, functionality that other people have that can be brought in. Scripting that people can do because they did a task once, they now know what the configuration of tools is and what the sequence of operations is. And if you save the configuration and perhaps do scripting to automate what you did by hand, you now have a workbench environment. You have a setup for doing a particular task in the molecular systems engineering you were doing. So plugins, modeling and design, workbenches, UIs, tool sets, educational and game content. If you start working with the Godot community, you find people saying, I know how to make this into a compelling game. Okay, we'll do it. Some things on wiki content, that's another story. But building up a designed and validated repository of components and systems is a major part of the objective here, as well as supporting people who are actually building things in the lab. And that in turn supports, again, activities ranging from a range of computational chemistry workflows through games and education, and bracketed in between are the molecular systems engineers, and for the long-term molecular systems engineering, the stand-ins who will be the citizen scientist engineers. So picture, platform engine, extensions to make it a molecular systems engineering platform, toolkit, workbenches, task-focused UIs and tool sets, and a growing repository of products. So picture here is one in which you have mostly core team contributions in the lower left, and mostly community contributions above. And with respect to community contributions, I should emphasize the idea here isn't, here's this big thing, it doesn't do everything, it's going to, stone soup, you bring different things, and then it does something else. It's going to be a bunch of functionality. And added functionality, where it's a distinct chunk of functionality, like this is like embed CAD Nano in Maya, embed CAD Nano in MSEP. What does that look like? It looks like something that is branded as CAD Nano with a reference to the website and papers to cite. It's not the idea isn't to have these little contributions be hidden away, but to push forward attention and to make people responsible for their work in fixing bugs. Okay, status, newly funded after very long incubation, a lot of thought, but money flowing just this month. So ample initial funding from Astera, courtesy of a lot of work by Adam Marblestone, part of which was persuading me that perhaps I wanted to play a leadership role in something like this. And we have an excellent project manager, Hein Peter, HP. You should talk to him. He's here. He introduced himself earlier. So he's not a graduate student and who's learning computers, learning to program because he wants to program something that's useful in his PhD, in his dissertation. He's a professional software developer who's led million-dollar scale projects before and has a network of software engineers he's worked with. And so we're going to be building to and beyond in the next year about a half a dozen full-time equivalent software engineers. That's enough to get something done. And there's enough excitement out there that I think we're going to be getting a lot more than that done. And again, lots of parallel work to be done with strong community support, I think means that it will be possible to expand on that, build on that surface area rather rapidly. So finally, invitation to contribute. We need to understand what people need to do their work so that we can have a roadmap that leads to supporting that. We need help to build what you need, which includes help finding the software components and systems that can be usefully integrated. Help recruiting contributors and leadership. This project is going to need to build out leadership as well. At some point, we're going to need a full-time product manager, as they say in the software world, / project leader. And of course, development moves faster if we have more money, especially with many parallel tasks. We expect to have a demo at some point in not too many months in the future that will give some indication of where we're going. So with that, I will just say thank you and invite questions.
Yeah, thank you for sharing your vision. How do you see the integration with experiment, both in terms of obtaining data from experiment as well as feeding back to realization of some of those ideas?
Yeah, workflows that go through the experimental world and back in again. On this side of the interface with experiment, you have problems of keeping data aligned, the experimental data aligned with the simulation data, aligned with the model that generated it, and not getting confused about that. That's a database and consistency management kind of problem that burden could be taken on inside this framework, and in fact the mechanism should be there to do that because it's needed for a wide range of purposes. Beyond that, it's a question of very specific workflows. You know, how are you using your experimental data to update your models? How are you using your models to guide your experimentation? And that is something where the aim is to provide tools that make it easy to describe and implement those workflows, but we need you to tell us how that works, and perhaps you to direct the implementation, perhaps with some professional software engineering support to make that go well and be a good, solid, usable product.
I guess my question is related, but so isn't the bottleneck the actual synthesis of these machines more than the modeling?
The long-term strong covalent solid machines? Or,
I mean,
the
like
current generation?
Atomic scale machines.
Protein engineering and structural DNA?
I mean, like, so like, for example, like DNA is very easy to assemble because of the programmability, yes. and protein is made by cells.
Yes.
But so how do you actually synthesize these very complex...
You mean dense covalent solids, the ones that had the gears and so on?
Yeah, for example.
Yeah. The answer is that today you don't. We're in the process of building tools that will enable us to build tools that will enable us to build tools that will move into that domain. Part of the conceptual difficulty that people have had is that these machines are almost childishly simple. They look like macroscopic machines. You know, surely this is just some silly idea. Real molecules don't work like that. Physics tells us this is what you want to build if you could. Physics tells us that you can build this kind of thing if you have tools that are made of comparable, you know, materials of comparable stiffness and fine granularity, and you work with extremely reactive molecular fragments in construction. If you want to grow something like silicon or silicon carbide or diamond or graphene, those kinds of structures, the growth species tend to be small and highly reactive. How do you make that work? Well, chemists, when they want to direct reactivity, tend to use you know, the inherent differential reactivity of molecules, or they use protective groups. You can think of a machine doing positional synthesis as sort of the ultimate protecting group. The reactive molecule only touches the workpiece where it's supposed to. If you have adequate control of thermal vibration amplitudes, you can target one location rather than another with angstrom precision. If you have that, then you can use highly reactive molecular fragments that can form multiple covalent bonds in one deposition operation, which means you can build up these very rigid polycyclic structures. One does not want to try to do that today or tomorrow. Some people have looked at this and said, oh, we're going to go off and try to do it in ultra-high vacuum with STM. And because Eric said it was a good idea, and I've always said, no, I've always said that's a bad idea. Look at my first paper on the subject. It was 1981. It was at the root of the citation tree for protein engineering until people got tired of citing papers that old. Because I said, that's the way forward. And now we're getting there. Yes?
Wait.
I'm trying to be the devil's advocate here, obviously. So a lot of us can build wonderful structures, but nature doesn't use them. For example, nature doesn't use gears, with few exceptions. Nature doesn't use cis-trans isomerization for motion, with few exceptions. And yet nature does things that we would kill to do. So the question is, what do we want to do? And maybe that's what needs to be clarified, and then go back and see what are the things that we need to achieve to get to that goal.
Yeah. Backward chaining from goals is very much the way that one wants to proceed, abstractly speaking. Clarify the goal, find what the steps are necessary to get there, and the better your design environment is, the more one can have a complex target, have confidence that it would work if you made the parts, and back out from there and start working on parts that fit the large scheme instead of parts then sort of hoping they might be useful for something, though it's a good exercise to do that initially. But in terms of non-biological models, which is a grand example of using that methodology, why do our brains conduct electrical signals in little tubes full of salt water? We don't do that in our computers. We have nanoscale electronics, which is finer scale than synapses, and the signal transmission speeds are a healthy fraction of the speed of light instead of being measured in like single or double-digit meters per second. Why are our bones made of a mineral material that is deposited from aqueous solution rather than being, say, the strength of carbon fiber composite? Because we have evolutionary constraints. And those apply all the way through cellular architecture, molecular machine architecture. Protein is an amazing material, but in terms of its engineering properties, it is crap. It's low modulus, low stability, low strength. Well, actually, spider silk is kind of competitive with some very good engineering materials. But why do we have that? Well, it's made by ribosomes. Why ribosomes? Well, at some point back before the last universal common ancestor, the life stabilized on three base per codon system that worked with the 20 canonical amino acids, and that's what we do. And the cell is full of salt water because we came from the ocean. If you're not constrained to that, you end up with, you ask what does physics tell us, and you find that you can make materials and systems that are, by many engineering criteria, orders of magnitude better.
Sure, I understand that you want to make something that's better than what you can find in nature. But the point still remains, what is that thing that you want?
Tell me what application, and I might be able to say give you something in more detail.
Well, you suggest an application where we can get there and beat nature.
Oh, I already did.
Sorry.
Yeah, another time, yes.
Okay.
One more question.
I'd really like to talk about things that might be within reach of this community, that are stretch goals and could have an enormous medical impact. The word to tag for that is mechanosome. Think exosome, but with something complicated inside that can do some rudimentary computation and sensing.
So Eric, to follow up the comment from my colleague here, critical path analysis, what we need is not motivation in terms of the final product. I mean, even the crude things that we've got already are plenty of motivation. What we need is to work out how to build the machines, to make the machines, to make the machines. I mean, the tools you're developing will do that too, but what I'm suggesting is that should be the focus. If you want to speed things up, if you want to get the community, the world able to explore this technology, it's not what we're aiming at that we need to understand, it's how to make it.
I think that both are very important for reasons that are incommensurate. It's very hard to compare the value of a greater clarity of vision of long-term future. It's very hard to compare the value of that with more rapid progress and contributions to aiding the experimental design and test cycle. I think that both are important, and I think they're synergistic rather than interfering. This project is going to have surface area, and if we have enough funding, we can build out in both directions at the same time and share some of the work and tooling in the process.